Why, hello and welcome back to our final lecture in our probabilistic sensor model series. Remember, our learning objectives are to describe probabilistic measurement models, describe various types of sensors that we use on a mobile robot, to use ray casting to determine the probability of a given shape for a map given a robot's pose, kind of like mapping, devise a maximum likelihood for noise parameters for a measurement model in a mixture model. We've looked at this already, including the Gaussian distribution, a uniform model, as well as an exponentially decaying model, depending upon the type of error. Discuss likelihood fields measurement model for rangefinders, and then today describe map matching, beam-based, and feature-based measurement models. Recall that the content of this course comes from the text Probabilistic Robotics, written by Sebastian Thrun, Wolfram Burgard, and Dieter Fox. And in order to learn more about their course as well as the text, please go visit probabilisticrobotics.org. Let's get started. So some of the additional models of proximity sensors that we will explore today, including map matching, which you can do with sonar or a laser, where you generate a small local map from your sensor data and then try to match that local map to your global model somewhere in the world. It's also a way of doing localization. Scan matching, which you do with a laser, where the map is represented by a scan of endpoints and you match that scan to the map or the global model. And finally, feature-based, where you use sonar, laser, or vision in order to get distinct features about the world, such as a door, a hallway, or sensor data. Let's go take a look. So now let's explore a scan-based model. Recall that for a beam-based model, it did not have smooth edges for small obstacles, but rather edges, and it was not very efficient. So the idea was that instead of following along the beam, you could just check the endpoint. So this probability is a mixture of a Gaussian distribution with a mean at distance to the closest obstacle, a uniform distribution for random measurements, and a small uniform distribution for max range measurements. We saw all of this in the previous lecture. And again, we assumed that there was independence between the different components in order to simplify the computation. So in the scan-based model example, you have a map M with 3 obstacles. So here we have the 3 obstacles, which are the 2 round ones close to the robot and the square one a little bit further away. So then by using our Gaussian distribution, we know that the sensor data for each of these obstacles will look more like that image on the right, where we now represent some of that uncertainty with that grayed out area around each of the obstacles. So instead of one beam going outward from the obstacles, as we had in the beam-based model for the Gaussian distribution, now for the scan-based model, we model the obstacles using the Gaussian distribution, where it's centered from a probability of the obstacle instead of the robot, so it can be pre-computed. So that's the perspective now from the obstacle as opposed to from the beam coming from the robot sensor. So for the scan-based model example, when you have the probability, you will have a shape as shown here, where this now represents that the robot has scanned the environment and this is where it has discovered the obstacle. So the first thing you notice is there's a valley. That valley represents that small valley between the 2 round obstacles, and then it goes up to a larger peak, and that represents that center obstacle or that center round obstacle. And then it goes down to another valley, and that valley is between the center round obstacle and the square obstacle. And then that little uniform period right there on the right would represent that square obstacle. And then finally, anything that hits the max range, could be anywhere else in the world, could be anywhere in that black space, is shown by that far right peak. So here's an example of what this would look like. Let's say you have an occupancy grid map like in the San Jose Tech Museum as shown on the left. And then on the right, we have pre-computed the likelihood field of where we would see sensor measurements by using a Gaussian distribution over each of the occupied spaces in that map. And so now as the robot moves through the world and you get the sensor data, you now have a probability of a certain sensor reading given the map as well as the robot's location in that map. The other way to do it is scan matching. Scan matching extracts the likelihood field from the scan and then uses it to match to a different scan. And by matching those together, you can figure out where in the world the robot was when it took that reading. So I take the left scan, I try to match it to the right scan, and then I come up with the robot must have been in the lower right-hand corner when it collected that sensor data. So some of the properties of a scan-based model is that it's highly efficient because it can use a 2D table only where you compile all that data. You can smooth with respect to small changes in the robot position. It allows a gradient descent for scan matching as opposed to abruptly reading and then not reading a value as in the beam-based model. You can ignore the physical properties of the beams because we're doing it from the perspective of the obstacles. And will it work for ultrasound sensors is the question, as opposed to sonar. And those are the things you have to determine by looking at the analysis. So now let's talk about landmarks. So there are several kinds of landmarks that you could have in your world. There could be active beacons like a radio or GPS. There could be passive landmarks like visual or retroreflective. You could have a standard approach for finding where the robot is taking sensor data by looking at triangulation, which we've talked about already, between two different landmarks. Because the sensor can provide distance to the landmark, bearing or angle to the landmark, or it could be a combination of the two. So by using distance and bearing, you can do vision-based localization where you use visual features in the world in the image because you know what the map looks like. And now the robot can use those landmarks to navigate and localize when it detects one of those visual images. For example, RoboCup, which was a soccer-playing dog, the Aibo robot, used a camera and localization in order to determine where it was in the world because there were certain distinct features about the world. For example, the yellow and blue goals, or if you look at the poles around the arena that all have a different color signature, like blue on top, pink on the bottom, it could then use those visual signatures in order to localize itself so that if it had a certain sensor reading, it would know where it was in the world. So for our landmark detection model, we assume that the robot measures a distance d to a known landmark in the map and a bearing alpha to that same landmark. And this half circle now represents all the possible measurements to that landmark based upon the robot's position. So the question is, what is the probability of getting a certain sensor reading given the robot's pose and the map of the world, which includes the known landmark? So you can do this in terms of the sensor reading dz or in terms of the distance to the landmark and the bearing to the landmark, which compile that sensor reading. And note that this is all subject to error because the measurement or the sensor will have error. But for this simplified example, we're going to assume that there are no other obstacles in the area. So because of the Markov independence assumption, we can then write that probability as the probability of d given alpha, given the probability of the distance d given x and m times the probability of alpha given x and m. So we're going to assume that we have Gaussian error in the distance and angle measurement and that we're able to determine these noise parameters because we have modeled our sensor by collecting data and matching it to our Gaussian distribution model. So then our algorithm for landmark detection modeling is given by the following. We have the probability given z, x, and m, where we have a measurement with a landmark ID I with an angle alpha and a distance d to the robot's pose x, y, theta. And then we can use the Euclidean distance to find the expected distance d, which is the square root of mx of I minus x squared plus my of I minus y squared, where mx of I and my of I are the known location of the landmark in the world. And the expected bearing alpha is the arctangent of my of I minus y over mx of I minus x, which is the difference between the robot's pose and the location of the landmark in the world. So then finally, in order to find the probability of detecting this landmark, giving our sensor reading, we use a Gaussian probability where our mean is given by d hat minus d, where d is the distance reading that we found for our landmark from our sensor, and that's multiplied by the expected bearing alpha minus alpha, which is our sensor reading for the bearing. And both of those are then using a standard deviation that is our sensor noise error. So we return that product to get the probability of determining or detecting that landmark. So here are some examples of using that algorithm. Assume that the red represents our robot and we have 3 landmarks with circles around them as a means of showing the Gaussian noise showing the distance. So the bottom left landmark is represented by this Gaussian noise here. The bottom middle landmark is represented by this Gaussian noise circle. And the top middle landmark is represented by this Gaussian noise. So when you multiply those 3 probabilities together, you end up with this image at the bottom. And what that shows you is the possible locations of that robot when it was able to detect all 3 of those landmarks. And that was found by multiplying the 3 probabilities together to find the probability of detecting that landmark from the robot's possible locations. So now, if we look at this without including the uncertainty, but we are only going to do it based upon distance, you can now use the following trick. So assume that we have 2 landmarks at P1 and P2, and we want to determine the possible locations of our robot when it detected those landmarks. So we would make the circles around each of those, and we now can use the distance of the intersections of the circles as well as the distance between the 2 landmarks and the following formulas to find x and x prime. So we would get that x is equal to a squared plus d1 squared minus d2 squared over 2a, and y is equal to plus or minus the square root of d1 squared minus x squared. Because y can be positive or negative, that's where we end up with x and x prime as the 2 possible robot poses. So the intersection of the circles represents the 2 locations x and x prime where our robot could have been when it was able to detect those 2 landmarks. Now, what about if we do this for bearing with no uncertainty? So here, once again, we have 2 landmarks, but we only want to look at the bearing of where the robot could possibly be when it was able to detect both of those landmarks. So for this one, there's a circle of possible robot poses where the angle between the landmarks is shown as alpha. So every possible place the robot could be in the world where the angle would be alpha between those 2 landmarks is created with this semicircle, or not really semicircle, but this circle area. So that circle represents all of the places the robot could be in the world. And then the distance we can calculate between the 2 landmarks is given by the law of cosine. d1 squared equals z1 squared plus z2 squared minus 2z1 z2 cosine of alpha. What if we have now 3 landmarks? It gets a little bit more complicated, but we now would end up with 2 circles, one between P1 and P2, one between P2 and P3, and we then have a plot of all the possible places the robot could be where there's an angle of alpha between P1 and P2, and the other circle is a plot of all the possible places the robot could be where the bearing would be beta. And so now the robot's possible location in the world is given at that intersection between the 2 circles as shown here. And from there, we would come up with Z3, the distance to P3, Z1, the distance to Z1 to P1, and Z2, the distance to P2. And we now, once again, using the law of cosines, could find D1 squared, D2 squared, and D3 squared. So now, looking at bearings only with uncertainty, we model the uncertainty as these 2 circles, these concentric circles that would represent the uncertainty in the sensor reading. And we now could use those to estimate where the robot could have been when it took the measurements. So notice that there are many possible locations if we have 2 landmarks, but if we can triangulate on 3 landmarks, we now will see that this gold area are the possible places where the robot could be when it was able to detect landmarks 1, 2, and 3, because that would represent the intersection of these 2 circles. So most approaches attempt to find some type of estimation mean or some kind of confidence area by using a Gaussian of the sensor area to find the most probable area on the map where the measurement was most likely taken. So in summary of our probabilistic sensor models, we can explicitly model uncertainty in sensing, and it's key to be robust. So in many cases, we can come up with a good model, and it can be found by the following approach. Determine a parametric model of a noise-free measurement. Analyze what are the possible sources of noise. Then add adequate noise parameters, eventually mixed densities for the noise, like we had uniform, Gaussian, etc. And then learn and verify the parameters by fitting it to your model. And then that way you can determine your noise parameters and then find the likelihood of a measurement given some kind of probabilistic comparing of the actual with the expected measurement. And we will find that this will hold for most motion models as well, as we saw in a previous lecture. And it's extremely important to always be aware of the underlying assumptions, such as the one that we have for Markov independence assumption. And this concludes our lecture on probabilistic sensor models. I hope you've learned a lot. I hope you've enjoyed it. I know it gets intense, which means you may have to watch it a couple of times and you may have to take notes. Please come back. I hope you've enjoyed, and make it a robotastic day. Bye-bye.